Hello, Eric. Mr. Eric, how are you today?
Good.
Good. Okay. So today we talk about the sum, the maximum sum of a binary tree. Maximum sum of binary subtree. Okay. Subtree. Max subtree sum. Okay. So actually it's quite a bit special. Is that you're given a binary tree. Yeah. 1, 2, 3, and then let's say that it can contain negative number. So let's see. What's the how many subtrees are there? You know the subtree. Subtree. So you can pick any root and including all its descendants, right? Look, Eric, how many roots are in a binary tree?
1.
1, which is here. Doesn't have any parents, right? And how many leaves here?
2.
2. Doesn't have any kids, yeah? Alright? So how many subtrees are there? Unique subtrees. Come on, subtrees. Pick any. How many nodes can you pick? Yeah.
You can pick.
Big base. No. There are four nodes. Yeah. When you pick a node, it's a subtree. Alright. You pick 10 minus 10. It's a subtree. 3. It's a subtree. 3 and 10 minus 10. 1. Subtree.
4.
2 is the subtree. So 4. I just said 4. How many kinds of subtrees? How many different? 4. Yeah, because you pick each node. You pick each node as a root, then it becomes a unique subtree, right? Does it make sense? Yeah. Okay, so the subtree of minus 10 is minus 10, right? Right? The subtree of 3 is what? Look at here. Subtree of 3. The sum of a subtree is 3.
Minus 7.
The sum of subtree 2.
2.
The sum of subtree 1.
Minus 4.
Wow, you're quick. Yeah, minus 4, yes. And the subtree of empty thing?
0.
0, okay. So now we want to find out the maximum sum of the subtree in the binary tree. Okay, so that's what it, yeah. So how many ways can we traversing the tree, binary tree, or tree? 2. What are those?
Breadth search,
Depth search, breadth search, normally. But depth search, actually you can have the pre-order, in order, post order, reverse the order, yeah? Reverse in order, yeah? Something like that, right? Okay, we talk about the depth search. So what's depth search?
Go as deep as you can.
Going deep as you can, right? Going deep as you can. Okay, so now, recursively, the sum of any subtree is equal to the sum of the current node plus the sum of its left tree and the sum of its right tree. Am I right? Yeah, this is recursive definition. The binary tree is recursive definition. It's equals to, there's a root node and its left tree and the right tree. And we know that the sum of the subtree of this one, right, Eric? Look, the sum of subtree this one is equals to 1 plus the subtree of its left tree and plus subtree of its right tree, right? Am I right?
Yeah.
So in this case, we are recursively dividing the problem into a smaller problem, right? Because we want to calculate the subtree of this entire tree. But we know this one, the answer is 1 plus the left bit and the right bit. And this is recursion, right? Alright? Because now we are only interested in 2 parts. 2 and then, for example, the right tree is 3 plus minus 10 recursively, okay? So when we're doing this, we know we can keep the maximum of any subtree, right? The sum of any subtree when we're doing this recursion. Does it make sense? Yeah? Okay, let me do this. Define, let's do this called the max sum. Okay, and then we go a root.
Column.
Yeah. And then we need to have an answer here, okay? At the beginning, we set it to the negative infinity, which is minus what? Do you still remember? How we use it? Yeah, math. Math dot what?
Infinity.
Math dot inf. Yeah? Okay?
Yeah.
Now look, we define a depth search function inside this function, yeah? Root. And when the root is empty, we return 0, right? Yeah, am I right? Does it make sense? Because the empty root is 0, right? Is a 0. Okay, now because look, inside this function, we want to update this answer, right, Eric? Look, we want to update this answer. So which keyword are we using? Which keyword are we using? Answer. What do we need to put in front of it? Which keyword in order to reference this? If you're not putting this keyword, then if you say answer and the computer will think, okay, this answer is here. Which keyword? Which keyword? Remember? What? Non-local. Okay, non-local. Right?
Local.
Okay, now we got a value. X equal, this is the sum of the current subtree, equals to root of value, right? Plus what? I just told you, plus what?
Root.
What?
Root left.
Root of left. This is the integer value, plus what? We're going to recursively call. What should I put? What should I put? What's the recursion function? Root of value, and then the left bit and the right bit, yeah? And what's left bit? What's right bit? Here is root of left, and here is root of right. So what should I put there? The sum of the current subtree is equals to its value plus what? The left bit and plus the right bit. So what should I put here? Come on. Come on, understand it. Come on. Which one? Come on. Which function calling?
Root.
Root? Sorry? What? What?
DFS.
Yeah, come on, DFS. How hard would that be? Recursion, I just told you, the recursion is calling the the sum of left tree, the sum of right tree plus itself is the sum of the current tree, right? But now I got this, and then I need to update it. So answer equals max what? Eric, can you tell me? Max what? Answer equals max what?
Left, right.
Left? Come on, answer equals what? We want to keep the maximum of the sum. What? What are we doing here?
Answer.
Answer, and then which value?
Root.
Root is not a value. Root is the node. So what? What value? Yes, x is the sum, okay? And then return what? Return what?
Answer.
No. Answer.
DFS.
No. Return what? Return what? We are returning the sum. DFS.
The biggest one.
No. The biggest one is here, okay? The biggest one is here. We
Answer.
just updating, but we are not returning this one. We are returning what?
The max.
This function returns the sum of the current subtree. And which one is the sum of the current subtree? Which one is the sum?
X.
Yeah, return x. Yeah, we are just using the x to update the maximum subtree, maximum sum of the subtree. Okay, and then we can call this DFS root. Yeah, and then return what?
The
Return which
maximum.
one? Which one is the maximum? Come on.
Answer.
Answer. Come on. Does it make sense now? What's the time complexity? Oh, what? What's the time complexity? The n is the number of roots in the binary tree. What's the time complexity?
Then.
O n. Okay.
Then.
Complex complexity is also O n. Okay. Why is it O n? Because
Retake so.
no, actually it's OH, right? OH. H is the height of the. No. It's not OH. It's the O n. Yes, it's O n. Because we need to visit every node in the binary tree, right? We need to visit every node in the binary tree. So it doesn't matter if it's the tree is highly balanced or not, right? Does it make sense? Okay? Okay, what's here? Answer equals what?
Root.
Come on, write it. Understand it, not remembering it. Oh, come on. Well, and you need to tell me why you put that thing there, right? What? X equals what?
Root.
Okay, root, yeah. You don't need to write it so hard, just quickly. Faster.
Root.
Root of what?
Dot.
Yeah.
V
Value.
value.
It's value plus. So can you explain to me what's that line? X equals what? What does it mean? X equals. Alright. Okay. Can you explain to everybody? Yeah. So what's X?
The X is equals to the root dot value and the DFS of root dot right and root dot and the left and right tree.
So what's X? What's X in this function?
Sum.
The sum of the current subtree, right?
Yeah.
And then we need to keep updating the maximum sum of the X, right?
Yeah.
Yeah. Does it make sense? Yes.
Yeah.
Okay. Any questions? Any questions? Alright. Why this is working? Because look, every time the root, when you're calling, and when you're reaching the root, when you're reaching the leaf, you will return 0, right? Return 0. And then you calling back, then you will be the subtree, the root of value. So can I have a pen, please?
Okay.
So actually, because I just said the empty subtree has sum 0, so actually you need to, if answer is smaller than 0, it needs to return 0. So you'll be actually is max.
Yeah, that's what I said last time.
Answer 0. Okay, so that's a
See,
small
I told
mistake. Okay, but the whole thing, Eric, look, 1, 2, 3. Okay, let's see this. Okay, so just this is easy.
That's a
Eric,
word.
look, you're passing the rule, right?
Yeah.
And then you're going down because it's calling. It's calling that. Yeah, root the left to the right.
If it's all positive,
Yeah.
all of them.
Yeah, look, root the left, root the right. So when x will be equal to 3, equals to 4, and equals to 2 plus 3 plus 4, and equals to so when you're calling this recursion, you're calling this way, right, Eric?
Yeah.
But when you're reaching the leaf, you are returning the result in the reverse order. That's why this works, right? Because you're calculating this x in the reverse order due to recursion, right? The stack, yeah, first in last out. You calling, look, when you're calling the root, and you're going deep until you go into the leaf, and when you go into the leaves, you return 0, and you roll it back up. So you'll be 3, 4, and then you'll be 9, and then you go back to 10, right? Does it make sense? Okay. Okay, that's it for today.
Bye.